very much, Mr. Chairman. I come from the University of the Aegean. I would like to dedicate this presentation to my colleague Wolfgang Dietzel. Unfortunately, he's not here. He couldn't make it to travel up to Catania. And we will focus on the 2024 aluminum alloy and to check the effect of embrittlement, hydrogen embrittlement, for this alloy. So I will first give you a small introduction about where we're gonna test different aging procedures. Aging procedures of this alloy means that you have precipitation of S or theta prime particles or S prime particles that you have a trade-off in mechanical properties, especially in yield stress and ductility. But the profound mechanism is to block the slipping of the dislocations. If you create too many particles, then you block them and you have a peak strength, while tensile ductility is decreased. I will now shift to the corrosion problem. It's an experimental study. You see the real synergy in aircrafts are a synergy of fatigue, natural aging, and corrosion damage. Here we're gonna speak about the synergy number C. Unfortunately, we cannot cope all the degradation problems. Here you can see that corrosion is actually a large problem. Here is burst strike, impact, corrosion, and fatigue. We're casing on fatigue more. This is a typical exfoliation that we have in aircraft structures, and usually in riveted sections. How to simulate this existing corrosion? There are several ASTM standards. However, we used ASTM G34. We used this called EXCO test because as it is very aggressive. However, it simulates the petty corrosion that you just saw in the previous slide. You can see several. Resolution is not that good. You can find a lot of paper with the tensile probabilities against EXCO time, but here. You can see that, for example, here is a corrosion crack. Below the crack is the hydrogen diffusion. You can see some properties, fracture surfaces, and that the core is ductile. But here you can see that there is a synergistic effect of the notches and the corrosion-induced hydrogen embrittlement. Right now, in this case, we have selected small exfoliation exposure time so as to eliminate this parameter of corrosion notches and just to relate our results with the hydrogen embrittlement effect. So we have selected various artificial aging times. We corroded them. We performed, of course, the reference test. We also corroded them, and finally we concluded. I will try to. We used the tensile and fracture toughness specimens according to standards. Performed the EXCO test that you can find in our. I will shift to the mechanical testing. This is the cracks. We have marked the experiment, the test, and here you can see these are the corroded surfaces and how the crack grows into the corroded area. Now we'll shift to the tensile test. Here you can see it's the reference one. This is 0.5 hours exposure time, 1 hour, 2 hours, and then suddenly at 4 hours you have a stress drop. So this means this stress drop is mainly due to decrease of the thickness of the alloy. So therefore you have notches there. So we have selected these 2 hours just to corrode the next specimens. Here you can see some microstructural results. 1 hour, 2 hour, you have not essential pitting, but at 4 hours, as I already mentioned, you have a lot of corrosion products. So in 2 hours, you have a stress drop, essentially stress drop in yield stress, but in blue you can see that you have almost 30% decrease in elongation of fraction from here up to here. So that is 25, sorry. It's this 25% is too much for such exposure time. It's definitely due to hydrogen embrittlement. Now I will show you the results of the reference aged specimens without any corrosion at all. These are typical aging curves, meaning that with the increase in aging time for various temperatures, you have a peak, and that means you are in the peak aging area, here and here, and then you have the overaging effect, meaning is dealing with the distribution, the size of the S-type particles. But the most critical parameter is ductility, that you had the opposite effect against the yield stress. The peak aging is here is accompanied with a local minimum in tensile ductility. Here you can see the effect. This is the aged material, and with magenta color you can see the aged plus corroded. So you can vertically you can see the decrease in tensile ductility. As you can see here in the reference one, you have a 26% ductility drop, but in the peak aging you have a less ductility. This means that during peak aging, due to the formation, of course, of the S-type particles, the ductility decrease due to the corrosion is essentially less. This goes also for a different. This is a different temperature. Here we have noticed 14% decrease, and here in the higher temperature you have even higher. So this means all this decrease are mainly due to the S-type formation, and especially due to the interface of the S-type particles with the surrounding matrix. So this is a summing up of all the results. Here in black line you can see this is how yield stress goes. So it is essentially to point out the underaging and peak aging and overaging conditions. And here you can see the ductility decrease, meaning that if you can associate also with the presenting precipitation sequence, this means that when you have coherent particles, then the ductility decrease is less. I will now shift to the fracture toughness test, but it's something that we have investigated in, we have analyzed in before 1 month or something like that. So you can see these are the typical resistance curves. Here are the critical tensile factor. Usually you can see that it follows tensile ductility curves. And here we have something similar with tensile ductility, but you can see that in the peak aging, condition, critical stress density factor also have minimum decrease due to corrosion. This is an investigation still carried on. Regarding the degradation mechanism, here you can see that, for example, you had different patterns in the outer surfaces. For example, this is at the peak aging and this is at the overaging. You can see that the outer surface is more or less completely destroyed. However, this pattern didn't influence in depth the fracture toughness and tensile ductility. And here you can see how dangerous is the exfoliation corrosion in side surfaces. As you can see in the peak aging, you have more uniform corrosion field, And this also was the case, for example, in the overaging condition. I have another of conclusion, but I'm quite sure that you can all see it in our published papers, including this conference paper. And I would like to thank also the financial support of Archimedes project and Carsten and Volker from Helmholtz Gestal Center. Thank you very much.